Imagine a computer capable of performing 1 billion additions and multiplications every single second. If you used it to run the calculations required to train the largest language models, it wouldn't take a year. It wouldn't even take 10,000 years. It would take well over 100 million years. Despite that staggering scale, the actual task the machine is performing is straightforward. Imagine finding a movie script where the AI's lines have been torn off. A language model takes the surviving text and provides a sensible prediction for what word comes next, repeating this over and over until the dialogue is complete. The machine doesn't pick one definitive word. Instead, it evaluates every possible word in the dictionary and assigns each one a specific mathematical probability. If the model always chose the most likely word, the dialogue would feel rigid and predictable. To produce a more natural flow, the system is designed to occasionally select slightly less probable words at random, which is why you get a different answer every time you run the same prompt. The conversational flow we see in a chatbot is the result of a mathematical function repeatedly executing this single prediction at scale. To see how a system learns to make these guesses with such accuracy, hit the subscribe button. This scale is built on a massive volume of human thought. For a person to read the text used to train a model like GPT-3, reading nonstop 24 hours a day, it would take over 2,600 years. As the model processes this data, it adjusts its internal behavior through billions of continuous numerical values, called parameters. These act like tiny dials that dictate the probability the model assigns to any given word. No human ever sets these dials. When training begins, the parameters are assigned random values, meaning the model's first attempts at speech are nothing but pure gibberish. To improve, the system uses an algorithm called backpropagation. It hides the last word of a training example, makes a guess, and then compares that guess to the real word. It then tweaks all the parameters to make the correct word slightly more likely next time. Repeating this trial and error adjustment across trillions of examples is what allows a statistical engine to accurately predict text it has never encountered before. Before 2017, models processed text one word at a time. Modern architecture uses the transformer, which absorbs entire passages simultaneously in parallel. Since training only works with continuous values, it converts every word into a long list of numbers. Within the transformer, an operation called attention allows these separate lists of numbers to cross-reference one another. This gives every word a chance to refine its meaning based on surrounding words. For example, if context mentions a river, attention shifts the numerical values for bank to represent a geological feature rather than a financial institution. This parallel mathematical cross-referencing allows the model to navigate the deep ambiguities of language. By the time the data reaches the final layer, the math has captured enough context to handle nuances that previously required human comprehension. However, a model trained only to auto-complete the internet is not inherently a helpful assistant. It will just as easily mimic toxic or unhelpful patterns found in its training data. To address this, developers use reinforcement learning with human feedback. Human workers flag problematic predictions, and those corrections further tweak the parameters, nudging the model toward the answers users prefer. This human intervention acts as a final filter, molding a raw statistical engine into the polite, reliable interface we use today. These complex capabilities are an emergent phenomenon, sophisticated behaviors that arise spontaneously from the interaction of hundreds of billions of simple mathematical rules. The sheer scale of these interconnected parameters creates a system of such density that we cannot easily trace the logic of a single output. This scale makes the model a black box. It is currently impossible for the researchers who designed the framework to explain exactly why the model chose one specific word over another. Every response the model generates is a mathematical distillation of the patterns and structures found in the trillions of pages of human history it has processed. It is humanity's collective written record, reflected back at us through a computational lens. We are now building our future on digital systems that operate beyond our ability to decode. Leave a comment with your thoughts on where this leads, and like and subscribe to stay tuned for more.